Hey guys, in this video I'll show you some chemical reactions with such beautiful yellow shiny and at the same time highly toxic and radioactive crystals, uranyl nitrate. Like all uranium compounds, this salt has weak radioactivity. This is easy to confirm by placing a dosimeter near the substance. For instance, the radiation level near this amount of crystals measured approximately 50 microsieverts per hour, which is about 100 times the natural background level. However, for short-term exposure, if you are near the substance for several hours, the doses remain relatively small and this does not cause any danger. Radiation decreases with distance, and already at a distance of several centimeters, it's practically absent. This substance also has another very interesting property. It glows very brightly under ultraviolet light. And aqueous solutions of this substance also have fluorescence, proportional to the concentration of the dissolved uranium salt. The higher the concentration of uranyl nitrate in the solution, the brighter its fluorescence. Interestingly, melting uranyl nitrate eliminates its fluorescence. I also tested whether cooling it in liquid nitrogen affects the glow intensity. Unlike some substances that fluoresce more brightly when cooled, uranyl nitrate's glow remains unchanged. When strongly heated, uranyl nitrate decomposes, first forming orange uranium trioxide. Then uranium trioxide loses oxygen at temperatures above 500 degrees Celsius and is reduced to triuranium octoxide. Adding a sodium salt or sodium hydroxide solution to uranyl nitrate results in the formation of sodium diuranate, an orange precipitate and one of the rare insoluble sodium salts. A red precipitate of uranyl ferrocyanide forms when uranyl nitrate reacts with potassium ferrocyanide. Adding zinc to an acidified uranyl nitrate solution causes the yellow liquid to turn green as uranyl ions are reduced to uranium ions. With a few drops of hydrofluoric acid, green uranium tetrafluoride precipitates. Now let's explore uranium oxides, starting with uranium peroxide, a pale yellow compound. The synthesis of this substance is very simple. It's necessary to carefully add a 30% solution of hydrogen peroxide drop-wise to a boiling solution of uranyl nitrate. After filtering, washing and drying in a vacuum desiccator, uranium peroxide dihydrate is obtained, which is also radioactive like all uranium compounds. The next one is orange powder, is uranium trioxide. Let's try to obtain it. As you remember, at the beginning of the video I showed that this substance is formed by heating uranyl nitrate. To prevent overheating, you need to use a built-in hair dryer, and not an open flame of a blowtorch or some gas burner. When nitrogen dioxide stops being released, we can consider the decomposition complete. But the best way to obtain uranium trioxide is to carefully heat uranium peroxide dihydrate, the same substance that we synthesized in the last experiment. Alternatively, you can decompose yellow ammonium diuranate to obtain uranium trioxide. Now we have pure uranium trioxide, which looks like this. Lastly, let's synthesize uranium dioxide, a key material used as nuclear fuel in reactors. To obtain uranium dioxide, it's necessary to reduce uranium trioxide with carbon monoxide. To track the process, I bubble carbon monoxide through barium hydroxide solution, and we don't observe any reaction. I set up a slow stream of carbon monoxide and carefully heated the uranium trioxide. But when heated, carbon monoxide reacts with uranium trioxide, forming carbon dioxide, which then reacts with barium hydroxide to produce insoluble barium carbonate, turning the solution cloudy. Once the reaction finished, we have barium carbonate in the flask and uranium dioxide in the U-shaped tube. Now, to make sure the video title is not clickbait, and to answer the question I asked in the community tab, let's test uranium oxides with anhydrous hydrazine. With uranium dioxide, there was no visible reaction. Now let's repeat the same reaction with uranium trioxide and uranium peroxide. At first, it seemed that there would be no violent reaction with these oxides either, but with uranium peroxide, hydrazine did ignite. Although, to be honest, I expected the reaction to be much more violent. The flame in this reaction is so pale that it's only visible in low light. If we add a little light, we may not notice it at all. This video wouldn't be possible without the support of my patrons, whose contributions help cover the cost of reagents and equipment. A huge thanks to all of you! If you enjoy this type of unique chemical content and want to support my work, consider joining my Patreon community. Together we can continue creating amazing experiments. Thanks for watching, see you in the next video.